So far, for oscillators, we've looked at a single example, and that example was theta dot equals omega. And what happened in that example was that our angle went around a circle at a very steady pace. So I'm just adding circles to show the direction of our angular velocity at each location. And something that's important to note is whether we think about this location as 0 or 2 pi or 4 pi or 6 pi, etc., every time we get there, we're always getting the same velocity back from this equation. So this number is in fact constant, but more importantly, it's periodic 2 pi. So if I'm back at the same angle, no matter how I name that phase, I'm getting the same velocity. And that's really important for this type of system to be well defined. So a condition for this type of system to be well defined is that whatever we have on this side needs to be 2 pi periodic. For example, let's take a look at the system theta dot equals theta. Will this system work as an oscillator model? Well, when theta is equal to 0, my velocity at this location would be 0. But when theta is equal to 2 pi, my velocity at this location now is saying it's 2 pi. However, 0 and 2 pi are the same location. So no, this would not work as a phase, as a dynamical system describing phase. So what about theta dot equals sine theta? I'm gonna sketch the diagram for this system. So okay, let me pull up a blue pen, and we have a circle, and let's see. When theta is 0, theta dot sine of 0 is 0, so theta dot's actually 0. And when theta is pi over 2, sine is 1, so we're moving quickly in that direction. When theta is pi, we have another 0, and when theta is 3 pi over 2, we're moving, actually, sine is -1, so we're moving this way, and so it looks like this point is stable, the other point is unstable. Okay, and sine of 0 is equal to sine of 2 pi is equal to sine of 4 pi. Sine is 2 pi periodic, so whether I'm thinking of this point as pi over 4 or pi over 4 plus 16 pi or plus 2 pi, this is actually always giving me back the same velocity. So yes, this equation is well defined, and in fact, this type of system appears to be not exactly an oscillator, right? Because although we're looking at phase information, with this system, wherever I start, wherever my phase starts, I seem to be attracting to a particular fixed point. So this would be like if I started with a new moon, and the moon evolved towards a full moon, and then sort of stayed approaching a full moon forever. And if I started on this side of the new moon, I also approach the full moon forever. That's kind of fun. Let's also look at an example that gives us a chance to think about how a bifurcation would look in this kind of system. And so this example is theta dot equals sine theta minus r, where r is some parameter. It's a constant that we control. And so something important to notice is that, again, this side is 2 pi periodic. So whether I describe an angle as pi or 3 pi or 5 pi, etc., I would be getting the same theta dot for all of those values. Okay, to think about fixed points, I'm going to think about points where sine theta minus r equals 0, so where sine theta equals r. And to think about those, I'm actually just going to graph intersections. Here's sine theta, and I'm going to graph r on these same axes. So if I draw r, r could be up here, or it could be down here. Okay, so that's a range of values of r that I've just drawn in. And I think we can see that since we know that sine theta ranges from -1 to 1, for r values outside of the range -1 to 1, there's no intersection, meaning there are no fixed points. So for -1 greater than r, or 1 less than r, no fixed points. What happens to the system in those cases? Okay, in those two cases, let's see, if -1 is greater than r, so r is all the way down here, r is quite negative, and so sine theta minus that negative number is always going to be positive. So sine theta minus r is always positive, it's never 0, and if it's always positive, we put arrows on going this way. But let's think a little bit more about that, because let's say r is like somewhat close to -1. In that case, here when the two curves are close to each other, we're moving pretty slowly, while here when they're far from each other, we're moving pretty quickly. So at -pi/2, we're moving our most slowly, and at pi/2, we're moving our most quickly. And so I'm going to represent that by adding some extra arrows. Specifically, if I have 2 arrows, or even 3 arrows, I mean that I'm fast. And so I'm going to kind of reflect our relative speeds. We're quite slow down here, we're medium here, and over here, and we're fastest up here. Okay, that's the situation for when r is less than -1. What if r is just a little bit greater than 1? Okay, in this case, r is positive, and it's always bigger than sine theta, so when we subtract it, we're getting a negative number. So we always have a negative number. That means we're going in this direction around our phase plot. And let's see, when is it closest? When are we slowest? Right now, these two curves are closest together at pi/2. So we're slowest at pi/2. We're fastest at 3 pi/2. So let's go ahead and make us fastest at 3 pi/2, intermediate, and slow. Okay? So slow, intermediate, fast, intermediate, slow, intermediate, fast, intermediate, slow. Okay? So that's what's happening in this system for when r is outside of the range of -1 to 1. Think about what happens in between where I know there are fixed points. I'm actually just going to go ahead and make a bifurcation diagram. So here's r, here's theta star, the value of the phase at the fixed points, and I'm going to stick to a convention that I'm only going to draw theta, the fixed point values in between, say -pi and pi is quite convenient here. Okay, and so above 1 and below -1, I know there are no fixed points. And above 1, things are flowing downward, and below -1, things are flowing upward. In between them, I know there are fixed points. Where are the fixed points born? So when r is equal to -1, what value of theta do we have for the fixed points? Okay, that birth is happening at -pi/2. So I have fixed points appearing at -pi/2. And at what value do those disappear? Okay, the fixed points disappear, they coalesce and disappear as r goes up towards 1, and that happens at pi/2. Okay, in addition, when r is 0, I guess I kind of have 2 fixed points, but I kind of have 3 fixed points. So I have one at 0, that one's unique, but then I have one at pi/-pi, and pi and -pi are actually the same location on the circle, but I'm going to draw them both in, and it's going to be clear in a moment why I would want both the pi and the -pi in on the diagram. And now to kind of get the bifurcation curves onto this picture, let's just sort of think, okay, when r hits -1, that's when the fixed points first develop, and as r increases, one of the fixed points is going this way, and the other fixed point is going this way, and so I need curves that represent that. One of the fixed points is going down towards -pi, the other fixed point is going up towards 0. So that's sort of how the fixed points look. And then as we pass 0, that fixed point that started down here, it goes up towards here, and then it continues on up till where they annihilate. And in addition, we have that other fixed point, the negative pi / pi fixed point, and it comes down from above to approach the annihilation. So I don't have stability information on this diagram at the moment, but I do have the fixed points, and you can see that kind of, it's sort of weird, this branch got broken because of how I chose to draw the diagram. And then let's see, how should our arrows go? It seems like we could think about this more carefully, but it seems like in this area we're going up, and in this area we're going down, and in this area we're going up, down, up. So it looks like stable, unstable, stable. Okay, and so this is, I guess, a bifurcation diagram with parameter r, reasoning through all the different cases that happen with this phase portrait as r varies.